Hello everyone, this is Lenu. Welcome to Learnwizz. Hope you guys are doing well. In today's video, we are going to dive into chemical equilibrium. Okay, physical chemistry topic from grade 11. So make sure you stay till the end of the video. You will get some amazing tips and tricks. And don't forget to hit the subscribe button and ring the bell icon so you will never miss an update from us. So now let's get started. Yes. So what is an equilibrium? Equilibrium is a state of a reversible reaction. Okay, it's a state of reversible process, and there are some conditions for a system to be equilibrium. That is, equilibrium is possible only in closed system. Okay, the system must be closed. Imagine this is an equation: a plus b in equilibrium with, so both sides the arrow. So this means what? This is forward reaction. And what is this? This is the products combines and coming back to reactant. That is what? Backward reaction. And this is two opposing processes, right? Forward and backward reactions are two opposite processes. And in equilibrium, these opposing processes occur at the same rate. Okay, these opposing processes occur at same rate, and we can call them, the equilibrium is dynamic. Equilibrium is dynamic in nature. Okay, and in this equilibrium, all the measurable properties, like what measurable properties means, what? Temperature, pressure, concentration. Okay, all the measurable properties remains constant. Okay, measurable properties remains constant. That is the main point you must remember when you think about an equilibrium process. Okay, now let us discuss in detail. Let's consider two chemical reactants, A and B, are reacting together and forming C and D products. So we call these as reactants and these two as the products. Okay, so initially we know that before the starting of the reaction, there is only A and B, right? So A and B concentration will be maximum. So let us draw a graph of maximum. Concentration is plotted in y-axis and time. So we know that at the beginning of the reaction, from that is at the 0 point, time 0, the concentration of A and B will be maximum, right? As the time changes, what will happen? As the reaction proceeds, concentration of A and B starts decreasing, right? They starts decreasing and the concentration of C and D starts increasing. Okay, so let us draw a graph like this. Concentration of A and B start decreasing like this. Okay, and initially this is A or B. Okay, this is A or B, starts decreasing with the time. Concentration is decreasing with time. And what is happening to C and D? Initially their concentration was very less. Okay, very less. Concentration was very less. 0. No C and D were there initially. And when the reaction proceeds, what will happen? C and D starts forming and they will form. Okay, at a particular time, that means at equilibrium, that is, there is what is happening. You can see here the equilibrium. Rate of forward reaction and rate of backward reaction become equal. That the two reactions, reaction between A and B and the reaction between C and D becomes equal. And we then say the system is at what? Equilibrium. The system established the equilibrium. That is the thing. Okay. So the same state of equilibrium is reached when we start with C and D or with A or B. Okay. That means at equilibrium, we can finalize that the rate of forward reaction is equal to what? Rate of backward reaction. That is said to be equilibrium is dynamic in nature. Okay, yes. Now let us move on to, we have studied a law of mass action. Law of mass action. What is that law? States that law of mass action states that rate of a reaction, whatever rate of a reaction is proportional to, what is it proportional to according to law of mass action? Yes, proportional to the product of active mass of reactants. Active mass of reactants. Okay, so that is law of mass action. So we have to use this law when you arrive at the law of chemical equilibrium and equilibrium constant. Okay, let us work out with the law of chemical equilibrium. Law of chemical equilibrium. Okay, let us write down the equation AA. A moles of the reactant A reacts with B moles of reactant B, forming C moles of product C and D moles of product B. Okay, so according to law of mass action, rate of reaction, right? Let us consider the forward reaction and backward reactions. Okay, so rate of forward reaction, okay, forward reaction is directly proportional to what? Yes, it is proportional to active mass of the reactants, right? So this raised to that moles and B raised to its moles. Also, the rate of backward reaction is directly proportional to what? When it is backward reaction, it is very clear that C and D are the reactants, right? So C raised to C and D raised to D. Okay. So according to this is proportionality sign. How will you remove that proportionality sign? Yes, we can put a constant here. So you'll be getting rate of forward reaction is equal to a constant. I'm going to put Kf. And rate of backward reaction is equal to Kb. Okay. And at equilibrium, whenever equilibrium is reached, at equilibrium, what will happen? Rate of forward reaction is equal to rate of backward reaction. We already studied what is meaning by equilibrium, right? Forward reaction and backward reaction will be equal. So we can equate these two, right? Kf A raised to A times B raised to B is equal to Kb C raised to C and D raised to D. Okay, so taking the constant to one side, you will be getting Kf by Kb is equal to C raised to C times D raised to D by A raised to A, B raised to B. Okay, this is a constant value. So we can put a big constant as K. This is called as what? Equilibrium constant. Equilibrium constant K is equal to. So this is called as law of chemical equilibrium. Okay, let us do one example so it will be clear for you. For ammonia, NH3 plus 5O2 in equilibrium with 4NO plus 6H2O. Okay, so what is equilibrium constant for this reaction? How will you find? Yes, this is very easy. You have to write down the product in the numerator, okay, and reactants in the denominator. Okay, so this is law of chemical equilibrium. So we can find for any equation you can easily find the equilibrium constant Kc. Okay, yes. Then we have to study one another thing that is related to a very important trick you can easily find. Okay, so let us have an example. So we have to take the general equation. We have already said this is the general equation we are usually taking. Okay, and here equilibrium constant is K. So for this reaction we are taking the equilibrium constant as K. Okay, now I am going to reverse, that is a backward reaction, Cc plus DD in equilibrium with AA plus BB. So what will happen to this equilibrium constant? So new equilibrium is equal to 1 by K. Okay, yes. Now another thing, we are going to multiply throughout this equation with N. So N moles of AA plus N moles of BB in equilibrium with N moles of CC plus n moles of BD. So what will happen to the equilibrium constant K? It will become K raised to n. Okay, very important. Okay, then while doing problems, you have to use these things. Okay, yes. Now, one more thing. Just imagine equilibrium is established. A in equilibrium with B and B in equilibrium with C, and A in equilibrium with B, the equilibrium constant is K1. B in equilibrium with C, its equilibrium constant is K2. Then what will be the equilibrium when A is directly converted to C? It will be K1 times K2. Just multiplication. So this is K1, this is K2, means A to C will be K1 times K2. Okay. This is another short trick. Okay. Yes. Hope you understand this trick. Yes. Now, equilibrium constant in gaseous system. So if the system is gas, like we are having all gases, products and reactants, so it is better to express them in terms of pressure. So instead of Kc, we are writing in terms of Kp. Okay, pressure. And instead of concentration, all are gases, right? So we are taking them in terms of pressure. That is only difference. Okay, Pcc PdD by Pa times P. Only the difference is they are gaseous reactants and products. We have to express them in terms of pressure. That's it. Okay. Yes. Then there is some relation between Kp and Kc. Okay. Very important. Relation between Kp and Kc. So Kc, very important. Kp is equal to Kc RT raised to delta n. Relation between Kp and Kc are not equal. Okay. Kp is equal to Kc RT raised to delta n. And what is this R value? R value is a universal gas constant. Okay. Universal gas constant. And here T is the temperature. And what is this delta n? Very important. Delta n is the difference between number of moles of gaseous products. Very important point is gaseous. Gaseous products and gaseous reactants. Number of moles of gaseous reactants. Okay. So that is what we have to study here, relation between Kp and Kc. Okay. So using this equation, we can easily find one more thing. If what is happening to the delta n, if delta n is equal to 0, if this delta n in this equation is equal to 0, that means Kp is equal to Kc, right? Yes. If delta n is positive value, okay, if it is greater than 1, yeah, positive value, then who is greater? Kp will be greater than Kc, right? If it is negative, the just reverse. I'm not mentioning here, okay? If you know these two, it will be easy. Okay, Kp will be, just put the positive value in this equation, you will understand Kp is always greater than Kc. Okay, if delta n is negative, just reverse. If delta n is 0, means what? Kp and Kc are very equal. Okay, yes. Now, moving to the next equation, homogeneous and heterogeneous equilibrium. So, homogeneous and heterogeneous equilibrium means what? Homogeneous and heterogeneous. I will give you one example, so it will be completely clear for you. For example, N2 gas plus 3H2 gas in equilibrium with 2NH3 gas. You can see here, all reactants and products are in same phase, right? All reactants as well as products, same phase. That is, all are gases here. That is what is homogeneous. Okay. Then, so just imagine what is heterogeneous. There will be more than one phase, right? So H2 in the state of liquid is converted to H2O. water in gaseous. Okay, there are two phases, liquid and gas, right? More than one phase will be there. That is what heterogeneous equilibrium. Okay, and in this case of heterogeneous equilibria, they generally involve pure solids and liquids. Okay, whenever there is the involvement of pure solids and liquids in the reversible reaction, we are taking its molar concentration as constant. Okay, at a given temperature. For example, I will make you understand CaCO3, that is a solid. It's converted to CaO solid plus carbon dioxide gas. Okay, so here you can write the equilibrium constant as Kp is equal to what? The pressure of CaO times CO2, carbon dioxide. Okay, P of CaCO3. And you now know that this and these are solids, right? Yes. So this equilibrium constant is equal to, or you can say this, we can cancel these two because it's a solid, there is no pressure involved in the solids, right? So it is directly related to only what? Carbon dioxide. Okay, also Kc you can write, since it is a gas, I write like Kp. You can also write Kc as, if you are writing in the terms of Kc, it is related to concentration of carbon dioxide only. Okay, no others are involved because they are solids, pure solids. We are taking them as constant one. Okay, one more example I will make you do, and that is, yes, nickel. Nickel is a solid. It is given plus 4CO. It's a gas. And it's converted to NiCO4. It's a gas given. So you can write Kp is equal to pressure of what? NiCO4 over pressure of CO raised to 4. Only this is involved, nickel is not considered. Okay, so what are the important, this is equilibrium constant, how to write it? Importance of equilibrium constant lies very important equations. Kc and Kp are very important, and this is applicable, K is applicable only when the concentration of the reactants and product have attained constant value at equilibrium state. Okay, and this KCOKP, equilibrium constant, is very important. Next point, independent of what? Initial concentration. Whatever be the initial concentration of the reactants or product, it does not matter. Okay, what is the value at equilibrium? That is mattering. Okay, initial concentration of reactants and products. And one more important point is equilibrium constant varies with change in temperature. As the temperature changes, equilibrium constant always undergoing changes. If you know this K value, you will understand you can predict the extent of the reaction. That means if K is high, equilibrium constant Kc or Kp is high, means what? Good yield, right? Good yield of products. If K is low, what does it mean? Poor yield, right? That is the only thing. And the extent of the reaction, just you can understand the extent of reaction. And one more thing, you can predict the direction of reaction. Okay, you can predict what? Direction. And this is somewhat important. So we have one more equation, that is QC. What is QC? Is reaction quotient. Okay, reaction quotient. Reaction quotient means it is the value. It is the value of this same equation. Okay, equilibrium equation. CC dd by AABB. Same equation, but this is not at equilibrium. Okay, not at equilibrium. That is the only meaning. Okay, the ratio of the products or concentration of the products to the product or concentration of the reactant at any instant other than equilibrium. That is QC, that is reaction quotient. Okay, then you can easily find the direction of the reaction in case if QC is equal to KC means what? Reaction is equilibrium. Reaction is at equilibrium. That is the meaning. Both are equal means reaction is equilibrium. Okay. If QC is greater than KC, okay, or if QC is less than KC, so what is happening? Which direction? Then that is only I am going to mention. If QC is greater, that means the reaction is backward direction. Reaction is taking place in the direction of reactants. Okay, reactants are more forming. So here that is just opposite. This is forward reaction taking place. That is products are more formed. Okay, in the direction of product. That is the only thing you have to study here. Okay, yes, hope you are getting right. And one more thing related to equilibrium constant, reaction quotient, and Gibbs energy. That is the relation between Gibbs energy and equilibrium constant. Okay, so we know the equation delta G is equal to delta G0 plus RT ln QC. Okay, and at equilibrium, what will happen at equilibrium? At equilibrium, delta G is equal to 0. Gibbs energy is equal to 0, right? Gibbs energy is a non-spontaneous process, right? Delta G positive means that is non-spontaneous. If delta G is equal to 0, the process is at equilibrium. That means here QC will be equal to KC. So you can write delta G0 is equal to minus RT ln KC. Okay, so this is the equation that is connecting standard Gibbs energy change and this equilibrium constant. Okay, so problems will be coming from using this equation. Okay, yes. So thank you so much for watching. If you enjoyed this video and found it helpful, don't forget to give it a thumbs up and share it with your friends. Leave a comment below if you have any questions or suggestions for the future videos. And if you already, make sure to subscribe to Learnwizz and click the bell icon so you will never miss an update from us. So stay curious, keep learning, and we'll be seeing in the next video. Bye for now. Thanks for watching.